Hello everyone, and thanks for watching Edupedia World Videos. This is the second video in the topic Magnetic Properties of Matter, and we'll continue our study of the different type of materials: diamagnetic, paramagnetic and ferromagnetic. Now I'm going to introduce a little bit of different notation now. In electricity, the notation which we used was E is equal to E naught plus EP, right? E naught was the original electric field. Let's see the problem as well with what we are doing. We take a material, we introduce it in an external field E naught. E naught is what we control, right? And then that E naught obviously exists within the material, then there exists an EP within the material, and the net electric field will be the resultant of these two. EP will be induced because of E naught, right? And the net will be E, which is E naught plus EP. Right. So similarly, what we'll have in magnetism is the original electric field we'll actually call H. Now, why do we call it H? That's sort of a historical thing, so we'll not get into that right now. But H is called the magnetizing field intensity. Now except for a factor of mu naught, which we'll get to in a minute, it is basically the original magnetic field which we apply, right? Then we'll have I, which is the magnetization. This is the analog of polarization, and polarization is what creates EP, right? So magnetization is what will create the magnetic field, right? The magnetic field due to the induced thing. And B will be the net magnetic field, net or resultant. Right, so we've just changed the symbols a little bit. H is what we'll control, right? If we take a material, we'll put it in a magnetic intensity H. So H will still be in there. Because of H, there will be created an I. Now I, it might be away from H, anti-parallel, which is diamagnetism, or in the direction of H a small amount, which is paramagnetism, or in the direction of H by a big amount, which is ferromagnetism. So I will be because of H, and the resultant of I and H will give me B, right? But there's one small catch here, and again, I'm not able to tell you why we do this, but the only answer is it makes equations much simpler when we deal with advanced electromagnetism. So instead of the equation being B is equal to H plus I, which is what it would be if it was the analog of E is equal to E naught plus EP, again, I'll repeat this once more because this sometimes is confusing to students. We take a material, we put it in an electric field E naught. So E naught obviously exists inside as well. There's an electric field EP created, which is due to the polarization. The polarization is due to E naught, and the net electric field E is equal to E naught plus EP. Similarly, we take a material, we put it in a magnetic field intensity H. So H is inside. Now EP will always be opposite to E naught, but the nice property of magnetic materials is that it can be opposite, which is diamagnetism, towards, which is paramagnetism, and towards with a very huge magnitude, which is ferromagnetism. So one of these three will be I, which will be due to H, and the net resultant will be H plus I, which will be the sum of these two. Except the small catch is, this is not the equation is this, right? So H and I have the same dimensions, but the dimensions are not the same as B, right? Up till now we've been talking about magnetic field, and the reason for that is magnetic field is the natural thing after we've done talking about electric field, but the more fundamental quantity is the magnetizing field intensity, and they differ from magnetic field by a dimension of mu naught. So they're mathematically is just a value. Mu naught is just a number, it's a proportional constant value, right? But later we do this because if we don't do this, then we'll keep seeing mu naughts everywhere in advanced electromagnetics. You won't see that. But when we start talking about these equations in terms of divergence and curl, which is what you do when you get to college, then to avoid this mu naught coming everywhere, we just use this equation as opposed to B is equal to H plus I, right? So from this equation what we get is, if there is no material present, then H is equal to B by mu naught. If there is no material present, then obviously the resultant magnetic field will be equal to the original magnetic field because there is no induced magnetic field, except there will be a factor of mu naught. right? Now another equation, which is the more fundamental equation from which everything comes, is I is equal to chi times h. Right, this equation is about how the magnetic field is created in response to the original magnetic field. Right, now the only difference between these and B is a factor of mu naught, so I hope you won't worry about that now. Right, now chi is a small value less than 0 for diamagnets. Right, so minus 0.01, minus 0.02, something like that. So if it is minus 0.01, that means you have a magnetic field of 1 Tesla. You'll create an induced magnetic field of 0.01 Tesla in the opposite direction, and you'll get 0.99 Tesla in that direction, which is a slightly reduced magnetic field. These are the standard values used for diamagnetism. So X is less than 0, diamagnets. This is actually not X, this is a Greek symbol. It is pronounced chi and written as CHI. Right. It is greater than 0, obviously paramagnets, because in that it is in the same direction. What about ferromagnets? Well, the classification of ferromagnets is chi is much greater than 1. Chi is 10,000 or 20,000 or something like that. So even a small 1 Tesla magnetic field can induce a 10,000 Tesla magnetic field in a ferromagnetic material. Right? So chi is called the magnetic susceptibility. Again, now we'll start seeing a lot of parallels between electricity and magnetism. We saw electric susceptibility earlier. Now chi is called the magnetic susceptibility. Right, now let's again start with I is equal to chi h. So once we have B is equal to mu naught times h plus I can write I as chi h. Right, from that we get B, the resultant magnetic field, is equal to mu naught times 1 plus chi times h. Right, now 1 plus chi is called relative permeability, and that is also called mu r, which is basically mu by mu naught. Mu naught is the original and mu now is mu naught times 1 plus chi. So earlier what was mu naught has now been replaced by mu naught times 1 plus chi, and 1 plus chi will be slightly smaller than 1 if it's a diamagnet, slightly greater than 1 if it's a paramagnet, and a very high value if it's a ferromagnet. Right, so these are some other important terms. 1 plus chi, which is written often as mu r or mu by mu naught, is called relative permeability, and mu simply is called permeability. So we've sort of come full circle. When we started electric field, we started with the formula 1 by 4 pi epsilon naught, and later we saw that this was only for vacuum. If a material has a relative permittivity ER, then the net permittivity will be epsilon naught epsilon R, which can be written as simply epsilon. And so in materials, 1 by 4 pi epsilon naught became 1 by 4 pi epsilon. Similarly, when you have mu naught by 4 pi, then this is for vacuum. When you have another material, you multiply mu naught by mu r or 1 plus chi, and mu naught mu r can sometimes be written as mu. So instead of mu naught by 4 pi, you have mu by 4 pi when we come in a material. So mu naught and epsilon naught are of vacuum. Epsilon naught is the permittivity of vacuum. Mu naught is the permeability of vacuum. Epsilon r is relative permittivity. 1 plus chi or mu r is relative permeability. And epsilon is permittivity of any material, and mu is permeability of any material. Right? So this is the point where we actually see lots and lots of parallels between electricity and magnetism, and it's quite nice. Next we move on to something called Curie's Law, that was discovered by Madame Curie, and it tells us the variation of magnetic susceptibility chi with temperature. So first of all, chi, and this is not part of Curie's law, but chi is almost constant while changing temperature for diamagnets. That's because chi is extremely small anyway, so we don't see a lot of change in it. Right, so this is for diamagnets, chi is constant. For paramagnets, Madame Curie gave a law which was chi is equal to C by T. It is inversely proportional to the temperature. As you increase the temperature, the electric susceptibility decreases. C is called Curie's constant, and it doesn't have a specific value because it depends on the material. Right. So this is Curie's law for paramagnets. But she also gave a law for ferromagnets, and what that said was that ferromagnets behave like paramagnets above a certain temperature. And that temperature is called Tc, temperature Tc, Curie temperature, or sometimes called Curie point. And it's different for every material, but for every magnetic material there will be a Curie temperature. Below it behaves like a ferromagnet, but above which it actually behaves like a paramagnet and follows the equation chi is equal to C dash, a new constant, by T minus Tc. So this is the variation with temperature for diamagnets, this is the variation with temperature for paramagnets, and this is the variation with temperature above the Curie temperature for ferromagnets, where they actually do behave like paramagnets. Right. Now finally, a very important concept left is only applicable for ferromagnetic materials, and it is called hysteresis. Okay, just before that, one small thing. We talked about magnetic field lines and magnetic field lines for paramagnetic and diamagnetic materials. What are magnetic field lines for ferromagnetic materials? But they would look something like this. You would not even see any field lines outside the material because the magnetic field within the material is so much larger than the magnetic field outside. So they would basically absorb all the field lines within them, leaving none or very few field lines outside. Right? So that is what happens. That is the description of the magnetic field lines for ferromagnetic materials. Right? Now let's go back to hysteresis. What hysteresis is, it's a process occurring only in ferromagnets. This should be in, yeah. And it says that I in terms of H does not only depend on H, but the previous history as well. And this is something we've actually not seen up till now in all of physics, right? When we say V is equal to U plus AT, V is equal to U plus AT regardless of what happened in the previous times, right? When we say about Hooke's law, F is equal to Kx, that doesn't say F is equal to Kx provided before that it was at rest. That just means F is equal to Kx. But when it comes to ferromagnets, magnetization does not only depend on the magnetic field intensity, it also actually depends on the history, right? So what does that really mean? So let's do it graphically. So I'm going to plot the graph of I versus H. Initially we start from 0, that is, we don't apply any external magnetic field intensity and there is no magnetization. Then we increase the magnetic field intensity, and experimentally what is observed is that this is the path that is followed. So chi is not constant, it even changes actually with H, right? So this is the path that is followed. Now what happens if after this you bring the magnetic field intensity back to 0? If it did not depend on the previous history, then it would trace this original curve back, and when you brought the intensity back to 0, the magnetization would be 0. But that's not true for ferromagnets, because ferromagnets have so many domains which might be parallel to the magnetic field that they actually do not simply break down their order simply because we've turned off that magnetic field. We could turn off our original magnetic field, but they would still retain their magnetization. That's how strong the magnetization due to the exchange coupling of ferromagnets is. So if we start bringing it back, it will actually come through something like this. Actually, let me make a better figure. Yeah, it would go something like this, and while coming back it might come something like this. So we bring the magnetic intensity back to 0, but the magnetization is not 0, and this point is called IC. It is called the retentivity. And now we are talking about specific permanent magnets. Like ferromagnets are a type of permanent magnet, and every permanent magnet has a certain retentivity, which means you apply a magnetic field intensity, you create its magnetization, and then when you remove the magnetic field intensity, the magnetization does not go back to 0, it retains a certain value, and that's called the retentivity. What do you need to do to bring the magnetization to 0? You need to actually decrease the magnetic field in the opposite direction. You need to not just take it to 0, you need to put a magnetic field or magnetic field intensity in the opposite direction. So once you do that, this is the sort of path that is followed. And at this point, the magnetic field intensity is labeled HD, and it is called the coercive force. And as the name suggests, it is the force or the magnetic field intensity we would have to apply in the opposite direction to bring the magnetization back to 0. Right. Now if we just keep changing magnetic field again, once we decrease it further, it goes something like this, and then once we increase it further, it goes something like this. So finally this is the loop that is followed, and we never go back to the original value. So if you keep increasing and decreasing magnetic field, then it does not just go along to and fro on a path, it actually moves in a loop, and because this is going in the negative direction, there is a negative amount of work done, and energy is actually lost in these cases. Right. This is sort of similar to something we saw when we were talking about rubber versus metallic wires. If you increase and decrease the length of rubber and increase and decrease it, we will actually end up dissipating thermal energy because the process is not completely reversible. Similarly, if you increase and decrease the magnetization field intensity, it will not always come back to its original value. Every time you do that, in every loop, there will be some amount of energy lost. This loop, by the way, is called the hysteresis loop. Right, and this type of loop is there for every sort of permanent magnet. The only difference is that there is different characteristics of this loop. For example, for a permanent magnet like soft iron has a very specific property that the magnetization changes very quickly to magnetic field. It does not really retain its magnetic field a lot. So for soft iron, the loop would look something like this, a very thin loop. Right, this would be soft iron. As opposed to that, this is soft iron. As opposed to that, we would find for steel that steel actually has a high retentivity, and you need to have a high coercive force to bring the magnetization back to its original value. So for steel, it would look something like this. Right, as opposed to for soft iron. High retentivity, high coercive force, low retentivity, low coercive force. Right. And if you want a permanent magnet, then you would want a loop like this. That is why steel is generally used in permanent magnets, and for a permanent magnet we would want a large hysteresis loop, large area loop, because that would guarantee that we would have high retentivity and a high amount of coercive force. That means even if we take our original magnetic field back, or magnetization field intensity back, it would still retain its magnetization, and that's why we have permanent magnets which actually have their own magnetic field, even though we are not applying any external magnetic field, because that magnetic field has been retained from its original value. And to remove that magnetic field, you would have to apply a high amount of coercive force. As opposed to that, when we are talking about galvanometers, we've seen the working of galvanometers, and in galvanometers what we want is we have coils of wire, and they end up rotating because of the current. Now I talked about galvanometers and I told you that often we actually put a soft iron core within a galvanometer, and what does that do? So a soft iron core is a ferromagnetic material. So for example, if this is a solenoid and its magnetic field was mu naught Ni, once you put a soft iron core within the material of the solenoid, the magnetic field will be mu Ni, and it might be increased by a factor of thousands or 10,000s. So this is why when we are talking about galvanometers, we put a soft iron core in the middle, because that greatly increases the magnetic field. But for that we would want a type of magnetic material which responds very quickly to changes in current or changes in external magnetic field caused by the current. So that's why when we are talking about galvanometers, we use soft iron. So galvanometers are used for soft iron cores are used for galvanometer. Steel is used for permanent magnets or similar materials. When you want permanent magnets, you use material like steel, which have a high retentivity and high coercive force. When you want a galvanometer, you use a material like soft iron, which has a low retentivity and low magnetic force. That means that every loop it would lose a lot of energy, right? And a galvanometer essentially works on loops. It works on a torque, right? So yeah, this is it. Yeah, this completes magnetic properties of matter. Thank you.